Okay, so we're doing the first question. I messed up the first time. It's kind of like that my notes wrong. Alright, but so this time it's going to be correct. The constant for pressure, or the dimensional analysis for pressure, is m L -1 to the power -1 T inverse squared. And then for volume, it's usually L cubed, but since it's volume squared, it's going to be L to the power 6 because it is a length analysis. And then R is a constant for molar gas. I was able to find it online, the dimensional analysis for it. So it is m L squared T inverse squared K power -1 mole -1. T is temperature, so that would be K. That doesn't really, I'm not using that right now. Now, since we cannot add or subtract quantities of different dimensions, it ends up to pressure equaling A over volume squared. So it ends up being m L -1 T -2 A over L to the power 6. If we work this around, it becomes A equals dimensional analysis m L 5 T inverse squared. Alright, and the volume for these two ends up equaling B. Volume is just L cubed, so B L cubed. Alright, and then for question number 2, vector resolution. These are quite simple. I merely had a lot of difficulty with the first one. So I chose to just draw them out to make it a bit easier on myself. This is the Y, X, and it's at 60 degrees. So this would be 30 degrees at 12 newtons. So in order to find this out, I used SOHCAHTOA. I went ahead and did adjacent over hypotenuse, so that's cosine. To find out X, I did cosine 60 equals X over 12. All you do is you just you do cosine 60 and divide it by 12. That gets me to X equals 6. So 6. And then for Y, it's cosine 30 X over Y over 12, sorry. So for Y, I did cosine 30 equals Y over 12. That got me to 10.4. 10.4 newtons, of course. For the second one, it's at an angle of 20 degrees. So this right here would be 70 degrees. Same thing, same process using cosine. So I did cosine 20 equals x over, let's see, this is 15 newtons. So x over 15. Kind of uncomfortable. X over 15. The same process as this. That gets us to x equals 14.1. And for y, it's the same thing, cosine 70 over y over 15 equals y over 15. That gets us to y equals 5.13. Okay, for the third one, same thing as the first one, very similar, just kind of negative. 60 degrees, 30 degrees, 25 newtons. Same process. Cosine 60 equals x over 25. Cosine 60 divided by 25, x equals 12.5. Cosine 30 equals y over 25. Find out cosine 30, and then you go ahead and multiply by 25. So I've been saying divide, but you multiply by 25 to counter the division of it, and then that gets us to y equals 21.7. And that is question number 2. I found I couldn't find a whiteboard on the library. They're all taken up. So I decided to go buy some poster board and use that instead. I hope it's okay. Okay, so number 3, for projectile motion. For the first part A, we want to find the time in the air. Very simple. We use the formula T equals 2 velocity sine of angle over gravity. So for that one I did, if you fill it in, it's T equals 2, 60 sine of 20 over 9.8. I chose to do 9.8 instead of 10 to make it a bit more accurate. Put that into the calculator. It comes out to T equals 4.18 seconds. Okay. Now for B, the ball's maximum height, we simply use the formula again. H equals velocity squared sine of the angle squared over 2g. When we plug that in, Now we square the sine of 20. We don't square 20 and then sine it. It's very important. Over 2 gravity, which is 19.6. Put that in the calculator, let it solve it. H equals 21.48 meters. That will be the ball's maximum height. Now for number C, the horizontal distance that it travels before hitting the ground, that is the range. So for C, once again, it's another formula. It's velocity squared sine 2 of the angle over 9.8. When we fill these in, it becomes, range equals. So range equals, when we fill them in, (60) squared sine 40 over 9.8. Let the calculator solve that, plug it into the calculator, and the range is 236.1 meters. So that has solved A, B, and C. Now for D, on does your friend receive the ball? No, he does not receive the ball. The ball is in fact 136 meters behind him. 136 meters. I got that simply by subtracting the distance of the friend, which was 100 meters, by the range. So he either has to turn around and run, or he has to run backwards. And for E, the speed that he has to run, I simply got distance over time, 136 meters over 4.18 seconds, because that is the time that the ball is in the air, the time that it takes to travel, equals to 32.5 meters per second, which is very fast. He will not get the ball. Okay, now we're on question number 4. Where a rescue pilot is dropping a survival kit in their plane at an altitude of 2,000 meters with a forward velocity of 150 meters per second. I used a sketch to make this one a bit easier to understand for myself. So this is 2,000 meters of height and going forward at 150 meters per second. So in order to find the time that it would take for it to land, I used the formula given, where T equals square root of 2h over g. So T equals square root of 2h, 2 times height is going to be 4,000 over 9.8. T equals 20 0.2 seconds. And to find the range, it's very simple. It's quite simply the time times the velocity. So range time times velocity. So 20.2 times 150 meters per second came out to 3,030 meters. So they would have to drop it 3,030 meters ahead of the target. Okay. For question number 5, it's the one where the blocks are on the table, where we have to find the acceleration of the blocks and the tension in the string. I searched online for formulas of acceleration and formulas of tension. I was also able to find it with the Pearson textbook and also from my notes. So for this one, it's very simple again. We simply plug in with the formulas. Acceleration is mass O times gravity over mass 1 plus mass 2. We plug that in, 2.8, 9.8, 3.5, plus 2.8. So 2.8 is the mass of the smaller block that's being fallen, and 3.5 is the mass of the larger block. 9.8 is acceleration due to gravity. Plug it into the formula. The acceleration in the blocks as a total net acceleration equals to 4.4 meters per second. To find the tension in the string, I use the formula once again. Tension was mass 1 times acceleration. So 3.5 times 4.4. So the tension in the strings was 15 newtons. Alright, so question number 6 is Atwood's machine. It's 2 blocks connected to a string by a pulley. Once again, it's finding the acceleration of the masses. So it's a very similar formula to this one, except a little bit modified. There's another mass up on top. So acceleration equals m2 minus mass 1. Mass 2 is the heavier one, multiplied by gravity, over mass 1 plus mass 2. We fill those in. Plug that into the calculator, and it gives us 3.4 meters per second. Almost done. The video is getting pretty long. It's 20 minutes now. My knees are starting to hurt. Okay, so for number 7, it's a super dart with a mass of 30 grams traveling at 250 meters per second strikes a steel plate. It's basically asking for the magnitude of the impulse of the plate, total magnitude. I had to look online. I didn't know where to look in the book for this one, but I was able to find a formula for total magnitude of the impulse. Give us a weird little symbol. So number 7. Give us a weird little symbol equals mass net times velocity. So it was mass times final velocity minus initial velocity. To find those, I also had to calculate for the net, so I had to use the signs. So equal to mass times negative velocity sine of its angle minus velocity sine of its angle. It came out to 0.03 for the mass of the dart because I'm using kilograms. So I had to change it to negative 250 sine 30 minus 250 sine 30 equal to 7.5 newtons. I was fairly unsure about this equation. So you need the shadow to look at it. But I hope it's correct. Alright, so for number 8, it's the one where the pet lab mouse is on the track and jumps from one cart to the other. I negated friction to solve this problem. So I was able to find a formula again where final velocity equals mass 1 times velocity 1 plus mass plus, this is the object of the mouse, plus mass 2. Mass 1 and mass 2 are both carts, respectively, times velocity 2, the resulting velocity. So simply plugging those in, I was able to get negative 0.35, 0.91, 0.08 plus 0.25. And this is what we're solving for, by the way. So then, getting this all together, 0.3185, 0.33 equals to 0.33 velocity, the resulting velocity, 0.33. We work out the math. Second velocity equals 0.965 meters per second. So for number 9, it's the one with the metal balls at rest being hit by one another. Basically finding the total kinetic energy. To find the total kinetic energy before the collision, all I did was use the kinetic energy formula, which I'll put right here. It's half it is half of mass times velocity squared. So for number A, I plugged that in. And the video is getting kind of long, so I'll just give the answers. For A, I plugged the mass and the velocity in, gave me 16 joules. For B, I plugged them in, gave me 14 joules. And for C, to find the energy transferred, I found the difference between the two nets. So it gave me 10 joules. Again, to give an example, 0.5 mass, 2 kilogram velocity squared, hit by a 2 gram moving at 4. So velocity squared, 4 times 4, 16. 2 times 16, 32.5. It's going to be 16. And that's how I was able to find very simple equation. Now for the last question. Question number 10. It is gives us, it's the one with the chickens running in a circular path. Gives us the angular speed of 1.52 radians. Asks how long does it take the chicken to complete one revolution. I looked, found a very straightforward formula. It was this constant right here over W equals to 2 pi radians, or the circumference, divided by 1.52 equals to 4.134 seconds.